Hello, and now we're going to be going over the mini processor simulator that I wrote my freshman year. This is a project that simulates a mini processor called MySpim. I wrote it in the C programming language, and basically it takes in assembly code or MIPS assembly code and does it for you, kind of like a processor, using a single cycle data path. So here's the repo. It has examples on how you can execute the code, as well as a bunch of descriptions. Here's the project description PDF. We'll go through it real quick with you. Basically, we're creating this MySpim processor by hand. We will handle 12 different instructions in the test files that I'm given that I'll be able to give to you. We simulate 32 general purpose integer registers. We're not going to handle floating point instructions though. We've got about 64 kilobytes of memory for this. We're going to be doing big endian byte order, and we have different conditions where the program will halt if we see an illegal instruction, jumping to an address that's not word aligned, the address of load word or store word is not word aligned, or load half is not half word aligned, and then accessing data or jumping to an address that is beyond the end of a memory. So those are ones where we're just going to stop and not handle them. Here's a test file case. We're going to have different instructions. Here are the comments on what these mean over on the side. So each line is one instruction. You can see this is 2 illegal operations down here, so we're not going to be handling these. But these are things like adding unsigned, ORing immediately, branching on equal to, subtraction unsigned, stuff like that. Here's a jump test. So the simulation ends when an illegal instruction is encountered. We have branching as well as jumping. We have some different functions we filled in for the ALU control. We can do either addition, subtraction, and, or, not, stuff like that. And I'll go through a little bit with that with you as well. You can go through here and feel free to read this. It's pretty detailed. So here's a little bit of a trace of what the program will be doing. First, main calls loop, which calls step when the code S is entered at the prompt. Then we go through the instruction fetch. We fetch the instruction addressed by the PC from memory and write it to the instruction. If there's a halting condition, we'll stop, otherwise we keep going. There's the instruction partition, where we partition the instruction to the several parts. The opcode are 1, 2, 3, funct, offset, and jsect. We'll assign these by doing some bit shifting. To extract, for example, to extract the leftmost 6 bits of instructions, we'll shifting right 26 followed by extraction using a 6-bit mask consisting of bit value 1 for the rightmost 6 bits. We have an instruction decode, which will decode it using the opcode and see what kind of different type it is. If it's R type or something like that, we'll be using a switch based off the opcode to assign controls to each value. We can read from register. These will be reading the registers addressed from R1, R2 from register and write the read values to data 1 and 2. We can do sign extension. ALU operations on data 1 and 2 will be performed. We apply all of them and output the result to ALU result. So we'll have something like this going on, and then here's the actual ALU that's implementing the operations by the ALU control up there. A and B are 2 operands, so here's an addition example right there. We've got read write from memory and write register, and then lastly PC update, which is the last leg of the single cycle data path. So here's a couple different test files we have that are given to us. So we'll run through these steps and be able to see what they input and output. I've included a couple different ones. Ones that have illegal instructions at the end, so you'll be able to test to make sure they do and do not work. And here's some comments on it. So we initialize this register to that value, this register addressed to this value. We assign this to both that and that. We decrement it. We go to a loop. That's in that decimal. We store this word at this offset. We load a word. We jump to an address, and then here's an illegal instruction at the end. And our last test file, which is one of the ones that was actually graded on, I think. Just goes through and tests to make sure every single instruction works as they should, and then the illegal ones are halted. So now real quick we'll go through the code before we go through and execute the program. So here's the ALU control, which has the different cases, which we'll be doing addition, subtraction, less than unsigned, bitwise and, bitwise or, a less than 0, and bitwise not. And then 0 based on results. 1 if the ALU result is 0, otherwise we're just going to say 0, 0. Instruction fetch, if the PC is outside the range, then we're going to halt. That's outside the memory. Otherwise we're going to fetch the instruction from memory and write it to the instruction. Bitwise shift by 2 to get the instruction from memory. And here's the instruction partition where we're going to do some bitwise shifting by different numbers to get the upper bits. This is for opcode, R1, R2, R3, funct, offset, and JSEC. So you can look through that, make sure you understand it. Here's the instruction decode, where if we have an unused opcode, we're going to stop. So based off the switch, here's register type for the ALU op. We know what these values are. Here's or immediate, load word, store word, set less than immediate, branch equal to or greater than 0, jump, and then here's if we don't handle the opcode, we set that flag and go ahead and halt. Here's read register, which is just reading the registers addressed by R1, R2 from register and write the read values to data 1 and 2. We put register 1 and 2 into their own arrays. Sign extend, very simple. Here's the ALU operations for each of these that you'll see. Addition, subtraction, bitwise, set less than unsigned, etc. Here's the I type. Here's read write from memory. The address is bad. Here's our halting condition for the memory. And lastly, we've got write register, which is writing mem data and ALU results. And PC update. And then if there's a jump or a branch, we have a separate case. Otherwise, PC equals PC plus 4, which is in the project description. So now I'll go ahead and try and run the C program and show you what the results are. Alright, so now let's go ahead and go through some of the test examples that I have in the repo. When you run the file, you compile it like this: gcc object file, your object file, and then the two spimcore.c and project.c. After this, you do / like your object file name space your input file name. The test input files I have in there are all .asc. I also have them in another place in the test files folder where they're turned into .text, so you can actually read them pretty easily for human readable text. And basically you have to have them in the .asc format for them to run. So I'll show you how you do that. You do it like this. So say I compile it and I call it MySpim is my object file. I do /myspim test.asc. So here's the different commands that you can do when you compile and run it. R is to dump the register contents, M is to dump the memory contents, S is to just step forward the next instruction. I'll be doing that mostly. C will just run through the whole program at the end. That's really cool just to see if you want it to run to completion if it's a really long file. I'll be doing step by step. H is to check if the program is halted. That means if it's one of those 4 illegal instructions we said before. I for memory size, you can print the input file, display the control signals, and quit. So we'll just go ahead and go through the test files real quick. We've got 3 different ones in the repo. Basically what this instruction does is it takes this value of 100 and takes the value in this register 0 and puts the value of that inside this register 8. So we'll be taking 100 and assigning it to register 8, which is T0. 100 is 64 in hexadecimal. So for example, I'll run it and I'll show you. Here's the registers, the 32 registers that were defined. 0 is 0, and then this is register 1, 2, 3, 4, 5, 6, 7. Register 8 is T0, register 9 is T1, register 10 is T2, etc. And then down here, S0 is register 16. So these are the registers that we're actually going to be using in this specific program, is registers 8, 9, 10, and 16, which correlate to T0, T1, T2, and S0. So you'll see that. So we're just going to head and step through the next command and see right now, before T0 had nothing in its contents, but now it has the value of 64, which in hexadecimal is the value 100. So in the next step, we're going to take the value in this register and add it to the value in this register and store it in this register. So we'll take the value in 8, which is 100, we just did that in the earlier instruction, 100 plus 100 equals 200, and store 200 inside register 9. And 200 in hexadecimal is C8. So let's go ahead and step through that. And we can see now in the register 9, which is T1, we have the value C8. So let's go ahead and step again. You can go ahead and see the next one. We have 7F in T2. This is because we put 127, which is the value of 7F in hexadecimal, into the value of 10, or in the register 10. Next instruction is branch if equal to. Now registers 9 and 10, they are not equal, so we will not be branching to this branch next. We're just going to continue on with this next instruction. So we can go ahead and step, and now we're going to step again and look at the register. We see here that we're subtracting the values in registers 8 and 9. So we subtract the value of 8 from 9 and store it in 10. So 9 has 200, 8 has 100, so 200 minus 100 equals 100, and we store the value of 100 in 10. So now you see 10, which is T2, has the value of 100, which is 64 in hexadecimal, just like this right here. So we can see that it goes from 127, which is 7F, to 100. So now we can step again, and we're loading the word into register 9, this value. So if you want to know a little bit more about load word, here it is right here. So it would be basically loading the word at RAM address, the register plus the offset of 12 into the new register. That number gives the offset of the address into the new register. So now we're going to go ahead and step again. And you see this register 16 is S0. You see it goes from 0 to 1 because this next instruction says set less than. If 9 is less than 10, no. If 10 is less than 9, no, I was correct. If 9 is less than 10, sorry, then we're going to have that equal 1. Otherwise, equals 0. So we set it to 1 because 9 is now less than 10. You see here's register 9 and here's register 10. Value of 0, value of 100. Sometimes it's a little confusing to remember that which register number corresponds to which T, etc., etc. So we're going to go ahead and step. Let's check. So right now we're at the jump test. We finished instruction line 8 right here, and we're about to do number 9. We can see that we have not halted. Halting is false, so we'll step one more time. And now halt goes to true because we've reached this NOP, a legal instruction. So we can go ahead and quit. And I'll just run through the last two with you. This will initialize register 8 to 7, register 9 to 2. This will add those two together and put the value of 9 inside register 10. This will do a loop and decrement whatever's in register 8 by 2, because that's the value in register 9, and that's the value that we're decrementing by right here, and storing it back into this register 8. This will branch. This loads, or this ors this in decimal. This is a store word at this memory offset. This is load word, and this is jump to a specific address. And this is jump to register, which we do not take care of, so that's an illegal instruction in our case. And the last test case, which is the one I was graded on, go ahead and run through it yourself. It's very fun to kind of see how the program operates. You can see we assign the value of 100 into register 8, the value of 100 into register 9. We add those two values together to put 200 into register 10. We subtract these two. This has a value of 0, this has a value of 200. And now we'll get negative 200 in register 11. We'll add these two, which is going to put the value of 100 into register 12. We'll do adding these together. Oh, we're ANDing them, not adding them. That's why I paused, because I was a little bit confused. Sorry about that. Sometimes it's hard to see the one little letter difference. Then we'll do store word, load word, and then we'll do a bunch of set less than. We can see that is 11 less than 15? Well, in here it's negative 200 less than 200. Yes, so we'll put a 1. Is register contents 14 less than 15? 14 is 200, 15 is 200. No, they're not less than, they're actually equal, so we're going to put a 0. Is 17's contents, which is 0, less than 16's contents, which is 1? Yes, it is, so we're going to put a 1. Is 15, which is 200, less than negative 200? No, it's not, so we'll put a 0. Is 15, which is 200, less than 400? Yep, so it's a 1. And here's a set less than unsigned. These are immediates, and these are just regular set less thans. So the immediates is because we're not actually comparing it to another register, we're actually comparing it to a specific value. And the unsigns are saying we're taking this value and doing an unsigned, so whether it's negative doesn't matter. So the register contents of 0, is it less than 8? Yeah, it is, because it's 0 less than 100, because register 0 has content 0. It is, so we're going to assign it to 1. This one says register contents of 11, which is negative 200, is that less than register contents of 0, which is 0? Technically, negative 200 is less than 0 because it's unsigned. We're going to say no. So we're going to say 0. So this is a branch. If these are equal, and they are, 8 and 9 both contain a value of 100, so they're going to branch over one instruction, which is this illegal instruction, so we're not going to halt here. Then here's another one. This should not branch because 10 and 11 are different. They're not, so we're not going to skip this one. So we're going to go to this one. Branch if these are equal. And nope. And then this one. And they are. And so we're going to branch over this illegal instruction. We'll go to the jump. And we're going to jump over these two next illegal instructions and get to this last one, which is going to immediately add 10 and 11 together. So 10 is 200, 11 is negative 200, so that'll create a value of 0 in register 23. And that's it. So feel free to run the code on your own, go through the instructions, and have fun with it. Thanks for watching.